Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, we know that from the exhaust gas of any vehicle, a huge amount of heat is lost. The temperature at the exhaust gas is in the range of approximately 750 degrees centigrade. We can utilize this heat to produce voltage with a suitable application of Seebeck effect, and finally this voltage can be utilized to generate electricity using a Wheatstone bridge connection. Today in this video we'll show this application of Seebeck effect using SolidWorks flow simulation. This is the model. We have made this model using SolidWorks. For understanding the geometry, let us cut this model from top plane. This is the view. So what we have done is, in this model, exhaust gas from the vehicle will be passing from this input location, and this is the flow passage. So this is the exhaust end. And from this one we are providing cooling, and you can see the passage of cooling. It will be passing across this one. It will be like a cross flow heat exchanger. So you can see the process, and from this location we will provide liquid nitrogen at a temperature of -195 degrees centigrade, and in between we have provided two semiconductors, that means silicon and gallium arsenide. So this face of these semiconductors will be facing huge amount of heat, and the other face will be facing cooling because of nitrogen, right? So this is the model, and in this analysis our aim is to see the temperature difference at this end and this end. So if we get huge amount of temperature difference between the ends, then this heating difference can be utilized to produce high voltage, and this voltage can be utilized to generate electricity. Let us see the complete view of the model. We can see this is the complete things. So near the end of this copper container we have provided one plate, and at the end of the plate we have provided two semiconductors, silicon and gallium arsenide. This is silicon and this is gallium arsenide. This face will be providing huge amount of heat, and this face will be facing cooling effect. So because of this cooling and heating effect, there will be temperature difference in between the two surfaces, and this temperature difference can be utilized to produce voltage, and ultimately this voltage can be utilized to generate electricity. Okay, so without wasting time, let us start our simulation. This is the model. The leads have already been provided at the 4 different inlet and exit locations. This is the entry of hot flue gas, and this is the entry of cold nitrogen at a temperature of -195 degrees centigrade. Okay, let us see our simulation. First of all, we have to start our simulation from flow simulation, and the environment of flow simulation will be initiated with the wizard itself. Let us start from wizard, and we are keeping the name of the project as by default project number 3. Next to that, we have to select our unit system. Let us consider the unit system as SI, and if we want, we can create some user-defined unit or system also, but at this moment we are considering SI system. And as per normal practice, we will be taking temperature as degrees centigrade. Next to that, it will be an internal analysis, and definitely heat conduction in solids will be taken care of, and gravity will be also involved because hot flue gas has a tendency to go up, and the direction of gravity will be y, that is indicated from this one. So along y direction it will be -9.81 meter per second square, and along z direction it will be 0. Done. Next to that, we have to see the gases. Main constituent of flue gas will be consisting of nitrogen from the air, carbon dioxide and water vapor with different percentages. Nitrogen, it will be consisting of 74%, then it will be water vapor 13%, and carbon dioxide also 13%. We have selected carbon dioxide, water vapor and nitrogen as the constituent of flue gas. Next to that, we have to select liquid. Liquid will be nitrogen at -195 degrees centigrade. Next to that, we have to select that material for this model. We are having different types of material as copper, aluminum and semiconductors. So from here we'll select the default material as copper, and the other materials will be selected during application of boundary conditions. And from here we'll select default outer wall thermal conditions and roughness. Next to that, thermodynamic parameters, it will be pressure will be 1021325 Pascal and temperature will be 20 degrees centigrade. And if we see the concentration of flue gas, nitrogen will be 74% from the air, so its concentration is 0.74, and water vapor will be 13%, so its concentration is 0.13, and finally carbon dioxide will be also 0.13. So these are the main constituents of flue gas. And solid parameters, definitely the temperature of solid parameters, it will be 20 degrees centigrade. Done. Now let us finish this. You can see this is the computational domain, and fluid has already been generated inside this container. Next to that, we have to hide this computational domain. Let us hide it. Next, we have to apply the fluid subdomains, because we are having different types of fluids and all the fluids will be applied from different subdomains. For application of fluid subdomains, let us cut this model from top plane. Go and check. Initially, we'll provide hot flue gas from this inlet location, and it is consisting of carbon dioxide, water vapor and nitrogen, and percentage of that one has already been defined. The temperature of hot flue gas will be approximately 750 degrees centigrade, as it is coming from exhaust vehicle, so its temperature will be 750 degrees centigrade. Selected the location. Now you can see the domain. Let us rotate this one for understanding the domain of hot flue gas, right? So hot flue gas will be flowing from this end to the other end, and from this one we will be providing coolant, that means cold nitrogen at minus 195 degrees centigrade. It will be surrounding this container. Okay, go and check. Next to that, we have to apply the fluid subdomain for liquid nitrogen. Let us rotate this one a little bit for proper selection of fluid subdomain. Fluid subdomains, insert fluid subdomain, and we want to provide liquid in this case, so it will be nitrogen, and temperature of nitrogen will be minus 195 degrees centigrade. Let us select that location. So liquid nitrogen will be flowing from this one. Now we can rotate this for understanding the flow passage of nitrogen. See, so hot flue gas will be flowing from this direction and coolant will be flowing along this direction, right? And you can see the edges of the semiconductors will be facing two different faces. This edge will be facing high temperature and this other face will be facing less temperature. Because of this effect, it will be facing temperature difference at the two surfaces, right? So both the fluid subdomains have been defined. Green check. Next to that, we have to provide solid materials. Insert solid material. As we are having different types of material that to be applied separately. Predefined solids. Initially, you have to apply that copper for the hot flue gas container. Let us select the solid geometry. This one, copper is applied. Next to that, we have to apply different materials. Again, solid materials. Insert solid material. It will be aluminum for other objects. So we are selecting materials, metals. It will be aluminum. Let us select that different surfaces. I have selected one face. Second one is also selected. Third one is also selected. Fourth one, fifth one. So we have already selected different materials as aluminum. Next to that, we have to select the semiconductors, which are made up of silicon and gallium arsenide. So again, selecting materials, insert solid materials, predefined. It will be semiconductors, and you can select silicon for some material. The red colored materials are considered as silicon. So in the solid geometry, we have provided the names of those things as silicon. So selection will be better one. One silicon is selected, second part, third part, and final part. So 4 different surfaces of silicon is selected. Silicon 1, silicon 2, silicon 3, and silicon 4. All 4 surfaces of silicon has been selected. Next to that, we have to select gallium arsenide, solid materials, insert solid material, predefined. We have to select semiconductors, and in this case, we will select gallium arsenide, and those material has also been defined in the solid geometry as GA1, GA2, GA3, GA4. So we're selecting that material as GA1, GA2, GA3, and GA4. So all the materials have been selected and defined. Next to that, we have to apply boundary conditions, insert boundary condition, and we have to provide hot flue gas from this opening at a rate of 0.2 kg per second. Let us select that location. And thermodynamic parameters, we can see it will be flue gas at a temperature of 750 degrees centigrade, and substance concentration, I can check it. It will be nitrogen with 74%, water vapor 13%, and carbon dioxide 13%. Green check. Next to that, you have to apply another boundary condition, that means for liquid nitrogen, insert boundary condition, and in this case our mass rate will be little less. We are considering mass rate of liquid nitrogen to be 0.01 kg per second from this location, and let us select that property. It will be nitrogen at a temperature of -195 degrees centigrade. Green check. Next to that, we have to apply boundary conditions, atmospheric pressure or environmental pressure at the exit locations. Again, insert boundary conditions. It will be environmental pressure at the exit locations. Let us select this one in a better way. Selected. Green check. Another boundary condition is needed. Insert boundary condition. It will be environmental pressure at this exit location of liquid nitrogen. Selected. Green check. So all the boundary conditions have been defined. Next to that, you have to provide some goals. Definitely the goals will be in the form of surface goals. So insert goals. You want to have surface goals at the 2 exit locations of hot flue gas and cold nitrogen liquid also. You want to have temperature of fluid at the exit locations. So it will be average temperature of fluid at the exit locations. We can select the locations by rotating a little bit. This is the hot exit of flue gas. Select other, lead number 4 selected. This is phase 1, and again we have to select this location. Let us rotate a little bit. This is the exit location of cold nitrogen. Okay, so directly you can select the inlet location. Selected. Phase 1 and phase 2 selected. You want to create goal for each surface separately. Selected. Green check. And we can provide names to these things differently. Like this is the phase 1, that means hot flue gas exit location. We can rename this one as temperature at hot flue outlet. THA4, temperature at hot flue outlet. Done. The second one will be renamed as temperature at cold nitrogen outlet. Defined. These two are defined. Now we have to see the surface temperature at the different silicon and gallium arsenide locations. So we can see this is the location of hot flue gas, and after this hot flue gas we have provided one separate metallic plate to connect this silicon and gallium arsenide. You can see it is connected in the form of a U-shaped object, right? So we have some metallic connection between the 2 semiconductors. So in this way we have to get the temperature difference at silicon and gallium surface only. Okay, so we need not take the temperature at the back side because it is already connected with the metallic plate, right? So we need to take the temperature difference between these two surfaces for the set of complete 4 numbers of silicon and gallium arsenide. Okay, so we have to select surface goals again. Goals, insert surface goal. We want to have average total temperature. Initially we will take the temperature for all these silicon surfaces. We select one proper way, that means the sequence will be anti-clockwise direction. This one will be first, second, third and fourth. Similarly for gallium also we will select the same sequence. Let us select silicon surface 1, surface 2. Now we can rotate a little bit for proper selection. Silicon surface 3 selected, and finally silicon surface 4. We have selected 4 different surfaces of silicon and we want to create goals for each surface separately. Green check, and we can rename these things as temperature at silicon surface 1. We can rename this one as temperature at silicon surface 1 TSI1. Second one will be temperature at silicon surface 2. Third one will be temperature at silicon surface 3. And the last one will be temperature at silicon surface 4. Done. Exactly same way we have to select the surface temperatures of gallium arsenide also. Let us rotate a little bit for proper selection. Gallium arsenide also we have to select the same sequence. We will be selecting this one as the first gallium surface, this will be second, this is third, and this one will be the fourth gallium surface, right? So again we are selecting some surface goals. Insert surface goals. We want to take average temperature of solid. Selected surface 1. Now we can rotate a little bit to select the other surfaces also. Second surface also selected. This is the third surface, and the last one is needed to be selected. Let us select a little bit by rotating. We have selected all the surfaces of gallium as phase 1, phase 2, phase 3 and phase 4, and we are going to create goal for each of them separately. Green check, and we can rename like previous case. It will be temperature at gallium surface 1 TGA1. Second one will be temperature at gallium surface 2, that means TGA2. Third one will be temperature at gallium surface 3, that is TGA3, and the last one will be temperature at gallium surface 4, that is TGA4. All the goals defined. Next one, we have to find that temperature difference in between silicon and gallium arsenide. That means we have to create some equation goals. Again, goals. Insert equation goals. And the equation goals will be obtained from the predetermined goals itself. As we don't know the temperature at which surface is more, that's why we want to have a absolute temperature difference between this gallium arsenide and silicon. We'll define the goals as an absolute form. Let's start from bracket, absolute bracket, and it will be starting from temperature at silicon surface 1 minus temperature at gallium surface 1. Bracket closed. Green check. Similarly for second one we have to have the temperature difference. Again equation goals to be obtained. Insert equation goals. It will be obtained from the predetermined goals. So bracket absolute bracket, it will be temperature at silicon surface 2 minus temperature at gallium surface 2. Bracket closed. Third equation goal is needed. Insert equation goal. Goals will be obtained from predetermined goals. We want absolute goals to be formed. So bracket absolute bracket temperature at silicon surface 3 minus temperature at gallium surface 3, bracket closed, green check. Last equation goal is needed, so insert equation goal. It will be obtained from the predetermined goals. When the goals to be obtained in absolute form, so bracket absolute, bracket temperature at silicon surface 4 minus temperature at gallium surface 4, bracket closed, go and check. So these are the different equation goals. We can rename this one as temperature difference 1, second one will be temperature difference 2, third one will be temperature difference 3, and the last one will be temperature difference 4. Now from these 4 we can have an equation goal again as average temperature difference, right? So the final equation goal as insert equation goal, it will be obtained from the predetermined goals. So we are adding the goals from here, and we have to have an average temperature difference. So it will be obtained from the temperature difference only. Starting from here, bracket temperature difference 1 plus temperature difference 2 plus temperature difference 3 plus temperature difference 4, bracket closed, divided by 4. That will provide average temperature difference on these sets. Again check. So we can rename this one as average temperature difference. So all the goals have been defined. Next we have to run this simulation. Before that we can have the complete model, because some parts of the model we have made hidden. We have to make all the parts to be completely visible, right? So we can go back to the geometry again. This is the geometry. From the geometry we'll make the different parts to be visible. Now all the parts are visible. We can run this simulation. Let us run it. We can start a new calculation. Let's run this. Solver window has already started iterations. It is preparing the model. Mesh generation is going on. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. We can see the solution is converged, and we have got all the results. All the results are converged. And from here you can see the exit temperature of cold nitrogen is minus 132.34 degrees centigrade, and for hot fluids it is 1302 degrees centigrade. And at different surfaces we got different temperatures, and we got temperature difference at the first surface is 82.5 degrees centigrade. Similarly for the second surface is 52 degrees centigrade, third surface is 104 degrees centigrade, and fourth surface is 123.72 degrees centigrade. So we are having different set of temperature ranges at different surfaces, right? And we got average temperature difference as 91.5 degrees centigrade. This is enough to have this Seebeck effect, and from this one we can produce electricity. Okay. Next to that we will see the goal plots in the form of graphs separately. And finally we'll go for some kind of optimization. In our case the mass flow rate of coolant was very less. It was 0.01 kg per second, and hot flue gas mass flow rate was very high. It was 0.2 kg per second. In the parametric study we'll change the mass flow rate of coolant and we'll make it very high, and we'll see the difference between the different surface temperatures. Okay, so let us close these things. Let us see the cut plots from different planes. When you see temperature distribution from front plane, it will be temperature of fluid. Let us see these things. As it is not completely transparent, we cannot see the temperature distribution properly. And let us see this one from front plane, and it will be a little bit of clear. You can see inside this one temperature is very high. This is indicating by red color, that is 1573 degrees centigrade. And as nitrogen is passing from right external end, so its temperature is very less. It is in the range of minus 197.4 degrees centigrade. As it is approaching, here it is getting more temperature, right? And at the exit location of nitrogen, its temperature is very less. Again, it is minus approximately 197 degrees centigrade. And in between at different surfaces, we are getting different temperature regions indicated by different colors, right? Let us see this one in the form of an animation. Let us play this. It will be flowing from front plane. You can see it inside this hot flue gas, its temperature is very high. It is in the range of red color. You can see heat flow, how it is occurring from different surfaces. Now we want to see the cut plots in the form of from right plane. Let us clear and hide these things. We want to see the cut plots from right plane. Insert cut plots, and instead of front plane, we want to see from right plane. Grid check. Let us rotate this one. We want to see from right plane. Let us play these things. Cut plot 2. Let us play. This is the hot flue gas entry. Its color is red. Okay. Let us clear and hide these things. Fine. Next to that, we want to see the surface plots. Insert surface plots. We want to see all surfaces. Temperature of fluid, green check. You can see at different surfaces, this is the cold nitrogen surface. It is having temperature in the range of minus 197.4 degrees centigrade, and this is the temperature for hot flue gas. We are having high temperature. It is in the range of 1573 degrees centigrade. Similarly, backside we can check it. Exit of hot flue gas is also very high temperature, and similarly exit of cold nitrogen is also less temperature. In between other surfaces, we are having different temperature ranges, right? That is indicated by the color change. Right here you can see different colors. That means we are having different temperature ranges at different locations. Okay. Let us clear and hide these things. Next to that, we want to see the dynamics of flow particles, that is how the particles will be moving from one surface to another surface, right? So, flow trajectories, insert flow trajectories. You want to see the dynamics of flow particles from all the different surfaces. Instead of 20 numbers, we'll make it 100, and instead of pipes, we want to see in the form of arrows only. Right? Let us select different surfaces. Select other. Lead number 2 is selected. Next, we can rotate a little bit and select the other surfaces. Select other. Lead number 1 is selected. Again, we can rotate a little bit to see the back surfaces also. Actually, all surfaces are not needed. We have to see only 2 surfaces only. For accuracy, you can select all the surfaces also, right? Okay. Select other. This lead number 4 selected. Now the last one is needed. That means this surface we can rotate a little bit. This is lid number 3. Select other. Lid number 3 is selected. So all the faces, phase 1, phase 2, phase 3, phase 4 selected. And from these different surfaces, you want to see the dynamics of flow particles in the form of arrows. Okay, green check. The particle study is running right now. We can see the dynamics of flow particles within a short time. Okay, it is done. Now you can see from front plane. Let us see these dynamics of flow particles in the form of an animation. Flow trajectories, let us play. You can see the flow particles of nitrogen liquid. Maximum nitrogen particles are coming from downwards. And from inside, you can see the flow particles, how the hot flue gas is passing from the inside chamber. Okay, let us clear and hide these things. Next to that, we want to see the goal plots. Insert. You can see all the goals, and that can be exported to Excel for better analysis. Let us export these things to Excel. We can have a graph of average temperature difference. So this is the graph of average temperature difference obtained from equation goals. Average temperature difference is in the range of 90 degrees centigrade, right? And temperature difference 4, we can see here. Temperature difference 4 at surface 4 is equal to 120 degrees centigrade approximately. And temperature difference 3 is 100 degrees centigrade. Temperature difference at the surface 2 is 60 degrees centigrade, and for temperature difference at the surface 1 is again 80 degrees centigrade. This is the temperature at gallium surface 4. It is more than 1100 degrees centigrade. You can see here its temperature is 1090 degrees centigrade, and this is the temperature at gallium surface 3. It is 1113 degrees centigrade. This is temperature at gallium surface 2. It is approximately 1172 degrees centigrade, and this is the temperature at gallium surface 1. Again, it is approximately 1099 degrees centigrade. Next to that, we will see the temperature at silicon surfaces also. First one is the silicon surface temperature at surface 4. It is 1214 degrees centigrade. Temperature at silicon surface 3 is also approximately 1218 degrees centigrade. Temperature at silicon surface 2 is also 1227 degrees centigrade, and temperature at silicon surface 1 is 1181 degrees centigrade. And next one, we can see temperature at the cooled nitrogen outlet. It is in the range of minus of 132 degrees centigrade, right? And finally, temperature at the hot flue gas outlet, it is actually in the range of 1302 degrees centigrade. Initially, its temperature was 750 degrees centigrade, and finally, after 180 numbers of iterations, we got the final temperature of hot flue gas as 1302 degrees centigrade. We can plot this data separately and we can go for detailed analysis, right? Next to that, we want to go for some kind of parametric study by varying the mass flow rate of cooled nitrogen. Okay, instead of that, we can see these things in the form of graph from here also, but we have already seen these things in the form of solver window. That's why we have exported this thing in Excel. Okay, next to that, we want to go for some kind of parametric study by varying the mass flow rate of cooled nitrogen. So solve, we want to go for new parametric study, and in this parametric study we want to go for design of experiments and optimization. And while designing these things, we have to depend on input variables. Input variables may come from the geometry or may be obtained from the boundary conditions. Here in this case, we are planning to have the input variables from the boundary conditions. That means we want to have mass flow rate of coolant nitrogen to be as the variable one. Inlet mass flow rate, it was selected as 0.01 kg per second. We'll change this one. Let us select the mass flow rate of nitrogen as the input variable. Green check. Its value was initially 0.01 kg per second. Now in this analysis we want to increase the mass flow rate of liquid nitrogen. Okay, so we have to vary this level. Let us change the level from 0.1 kg to 0.5 kg. And let us see the difference. We have varied the range of liquid coolant mass flow rate. Let us see the output parameters. It will be obtained from the goals. We have a lot of goals. We can have all the goals. Let us select all the goals. That means we want to see all the goals with varied mass flow rate of coolant. Okay, let us see the scenarios. 5 numbers of experiments have been defined. Let us create all those things. So we have defined the mass flow rate at different levels. Let us create those mass flow rate at a correct sequence, right? Initially we'll take the mass flow rate as 0.1 kg per second. Next one will be 0.2. Third mass flow rate we want to be 0.3 kg per second. Fourth one will be 0.4 kg per second, and the final one will be 0.5 kg per second. With this different mass flow rate, we'll have our goals and see the effects, right? Let us run these simulations. It is preparing the model and mesh generation is going on. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. Okay. The iterations are finished. We can see all the results are converged. Initially, the temperature difference was 111 when the mass flow rate of cold nitrogen was 0.1 kg per second, and when the mass flow rate was 0.2 kg per second, that temperature difference is 110, and when the mass flow rate is 0.3 kg per second, the average temperature difference is 115.4. So in this way, you can see that average temperature difference is not varying that much, but only the difference we can see here, that when the mass flow rate of cold nitrogen is increased, the temperature at the exit location of nitrogen is increasing. Initially, when the mass flow rate of cold nitrogen was 0.1 kg, in that case, average temperature at the exit location of nitrogen is minus 153 degrees centigrade, and when it is 0.2 kg per second, average temperature at the exit location of nitrogen is minus 173.12 degrees centigrade, and 0.3 mass flow rate, the average temperature is minus 178.8 degrees centigrade. When the mass flow rate is 0.4 kg per second, the average temperature is minus 182.2 degrees centigrade, and finally, when the mass flow rate of liquid nitrogen is 0.5 kg per second, then the exit location of nitrogen temperature is minus 184.89 degrees centigrade. But we cannot see that much of change in difference in temperature. The difference in temperature is varying very little amount. So this is all about our today's analysis. So with this analysis, what we got the temperature difference at the different surfaces of semiconductors, and the difference of temperature was in the range of approximately 100 degrees centigrade, right? With this one, we'll conclude our analysis. Instead of stopping it here, we can go for further studies. That means with the temperature difference, we can connect this one with voltage, and finally from the voltage we can generate electricity or current. Okay, for that we need to have some kind of mathematical calculations. We know that temperature difference is directly proportional to the voltage, and voltage equal to alpha into temperature difference, where alpha is actually constant known as Seebeck constant. That alpha is dependent on material properties. With further studies, we can find this relation between temperature difference and voltage, and from this voltage finally we can generate current or electricity. Okay, thank you so much for watching this. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.